All right, let's just jump right into this explainer. Today, we're looking at J. Robert Oppenheimer, Beyond the Atomic Bomb. We're going to completely reframe the legacy of a guy whose name is basically synonymous with, unprecedented destruction. So we are looking right past the mushroom clouds to uncover his foundational, honestly groundbreaking role in modern theoretical physics.
Now, you've probably asked yourself this at some point. What if Oppenheimer's greatest discovery wasn't actually the bomb? I mean, the whole world knows him as the father of the atomic bomb, right? But his true, lasting scientific legacy actually lies way up above us in the stars and deep down within the quantum realm. What if his most profound contributions to human knowledge had absolutely nothing to do with Los Alamos? To really get his genius, we've got to trace his path from being this erratic, brilliant student to becoming the absolute vanguard of theoretical physics.
Looking at this timeline, you can see Oppenheimer had a crazy, rapid, but highly turbulent academic rise. He started at Harvard in 1922, majoring in chemistry. And get this, to make up for some time he lost being sick, he actually took 6 courses a term instead of the usual 4. He just blazed right through, graduating summa cum laude in only 3 years. But that insane momentum hit a massive roadblock the second he crossed the Atlantic to study at the Cavendish Laboratory in Cambridge.
So his stint in England was honestly a total disaster. As a clumsy experimentalist at Cambridge, he was terrible at lab work, found it incredibly boring, and plunged into this really deep depression. He even developed a super antagonistic relationship with his tutor, but thankfully his salvation was waiting for him over in Germany. When he left Cambridge in 1926 for the University of Göttingen to study under Max Born, the transformation was literal night and day. He absolutely thrived at the theoretical chalkboard. He was so brilliantly confident that during his oral PhD exam, the administering professor joked that he was glad it was over because Oppenheimer was actually on the verge of questioning him.
And it was at Göttingen, at the crazy young age of 23, that he cranked out this monumental piece of work. Along with his advisor, Max Born, he published the Born-Oppenheimer approximation. Basically, this is a foundational mathematical treatment that neatly separates nuclear motion from electronic motion. It lets physicists effectively ignore the incredibly complex motion of the nucleus, which drastically simplifies their molecular calculations. And here's why you really need to care about this. This one mathematical treatment remains his most cited scientific work to this very day, literally his most cited paper.
Okay, moving right along into our first main section, the Berkeley Pied Piper, Forging American Theoretical Physics. So, having totally conquered Europe, Oppenheimer heads back to the States in 1929, snagging professorships at UC Berkeley and Caltech. And by doing this, he essentially imported the revolutionary new field of European quantum mechanics right to American shores. But he wasn't just some ordinary teacher in California. The guy was an absolute phenomenon. He had this hypnotic, mesmerizing presence. I mean, he was a polymath who loved reading ancient texts like the Bhagavad Gita and the original Sanskrit. He cultivated these deeply devoted graduate students who literally started copying his walk, his speech, his mannerisms. And intellectually, he could seamlessly guide a group through quantum electrodynamics, cosmic rays, and nuclear physics all in a single afternoon.
And his exquisite taste as an educator is captured just perfectly by his colleague, the fellow Nobel laureate Hans Bethe. Bethe noted that he always knew what were the important problems. He truly lived with those problems, struggling for a solution, and he communicated his concern to the group. Oppenheimer didn't just stand there teaching dry facts. He masterfully pinpointed the most pressing, mysterious physics problems of the day, lived and breathed them, and communicated that intense intellectual urgency to his students. He basically sparked a whole generation of American physicists.
So the really crucial takeaway here is how his sharp intuition just constantly put him ahead of the curve. Just look at the prediction of the positron in 1930. The brilliant physicist Paul Dirac had boldly asserted that these newly theorized positively charged electrons were actually protons. Well, Oppenheimer steps in with a razor-sharp rebuttal. Drawing on experimental evidence, he argued, nope, protons are simply too heavy. He realized the mysterious particle had to have the exact same mass as an electron. He essentially predicted the positron 2 full years before Carl David Anderson physically discovered it, a discovery, by the way, that won Anderson the Nobel Prize.
He just kept making these massive quantum leaps.
Fast forward to 1935, he partners up with his very first PhD student, Melba Phillips. Together, they cracked a huge nuclear physics puzzle about artificial radioactivity. See, when experimentalists were bombarding heavy nuclei with high-energy deuterons, the results just weren't matching the existing predictions at all. But the Oppenheimer-Phillips process solved it completely. And what's wild is that this mathematical theory is still actively being used in nuclear physics today. How cool is that?
All right, that brings us to our next section, Prophet of the Stars, exploring astrophysics. As the 1930s were wrapping up, Oppenheimer's intense focus shifted in a big way. He pulled his gaze away from the tiny subatomic world and looked straight up at the cosmos, churning out a series of just breathtaking astrophysics papers. Working alongside his student George Volkoff, he calculated this precise, theoretical boundary called the Tolman-Oppenheimer-Volkoff limit. Basically, this limit dictates the absolute maximum mass of a neutron star. Once a star gets too massive and crosses this line, it can't remain stable anymore and has absolutely no choice but to undergo complete and total gravitational collapse.
And then, by 1939, partnering with another brilliant student, Hartland Snyder, he took that concept to its terrifying logical conclusion. They mathematically mapped out the stability of stellar cores, step by step, and calculated exactly what happens when those cores hit that critical mass limit. They proved the phenomenon of continued gravitational contraction. Think about that for a second. Decades before the term was even invented, and way before telescopes could ever actually observe them, Oppenheimer mathematically proved the existence of black holes.
Now, despite all these world-altering discoveries, his actual working style was pretty unconventional. Nobel laureate Murray Gell-Mann pointed out that Oppenheimer totally lacked Sitzfleisch, which is this great German term that basically means sitting flesh, or, the patience to just sit in a chair for hours cranking out immensely long mathematical calculations. Instead, his real superpower was dropping these brilliant upper sous, these sudden piercing insights that instantly sparked entire fields of study for other scientists to go off and finish.
And honestly, that exact trait brings us to this number right here, 4. That is the total number of times J. Robert Oppenheimer was officially nominated for the Nobel Prize in Physics. He got nominated in 1946, 1951, 1955, and 1967. And yet, he never won. Not once. His intellectual interests just shifted way too rapidly for him to carry any one single topic to its absolute final fruition. He was the guy who planted the seeds, but he rarely stuck around to harvest the ultimate accolades.
Which leaves us with this final, kind of haunting thought. Had he lived to see black holes proven, would we remember him for the stars rather than the bomb? A lot of modern physicists strongly believe his pioneering work on gravitational collapse in black holes was unequivocally Nobel-worthy. If he just lived long enough to see his cosmic predictions proven true by modern astronomy, would his whole legacy be totally different? It really makes you wonder how history might have reframed this brilliant, turbulent mind. Not just as the destroyer of worlds, but as the guy who first illuminated the absolute darkest mysteries of our universe. So the big takeaway from this explainer is simple. His brilliance definitely did not begin or end in the New Mexico desert. His intellect shaped the very foundations of modern physics. Knowing what you know now, what do you think his greatest legacy really is?